Good morning, students. A warm welcome to you all. So today I start your syllabus with Unit 3, that is Ordinary Linear Differential Equations. I already sent the syllabus of Bsc IV semester to Google Classroom. I hope you all downloaded the syllabus. Okay, so let us start now. So linear differential equation with constant coefficient. So any differential equation of the form a0 dny by dx raised to n plus a1 dn minus 1 y by dx raised to n minus 1 plus a2 dn minus 2y by dx raised to n minus 2 dash dash up to a and y equal to f of x. So where this a0, a1, a2 and all a and r are constants, and this f of x is a function of x. So this type of a differential equation is known as a linear differential equation. A linear differential equation. So why it is called a linear differential equation means here both dependent variable, right? So both dependent variable and its derivative. So here what is the dependent variable? So dependent variable is y, okay, dependent variable is y and its derivative means dy by dx, right? So dependent variable means y, its derivative means dy by dx. So here both dependent variable say y, okay, and its derivative that is dy by dx or dny by dx or dn raised to n minus 1 y by dx raised to n minus 1. So all these are derivatives of this dependent variable y. Now see here y, the power of y is 1. Everywhere you see here, either you see here or you see here or you see here, the power of y is 1, means the degree of this dependent variable is 1, and similarly the degree of the derivative, so means dny by dx raised to n, its degree is equal to 1. Similarly here dn minus 1 y by dx raised to n minus 1 and its degree is also 1. So here both dependent variable and its derivative, they exist in first degree. They appear in first degree, or we can say that the degree of the dependent variable and its derivative is equal to 1. So therefore this is called as a linear differential equation with constant coefficient. Means here a0, a1, a2 and an all are constants, so therefore they are known as a linear differential equation with constant coefficients. Now in this, here this d by dx, it is known as a differential operator. Okay, so it is known as a differential operator and it is denoted by capital D. So d by dx is denoted by capital D. So then dy by dx, so dy by dx is denoted by capital dy, because dy dx is capital D. So dy by dx, it is denoted by capital dy. Similarly d square is denoted by d square by dx square, d cube is denoted by d cube by dx cube, and so on. Okay, so now by substituting all these in this derivative, okay, now see dn by dx raised to n means it is d raised to n, means by replacing this d by dx by its operator, that is capital D, and similarly here dn minus 1 by dx raised to n minus 1, it is replaced by d raised to n minus 1. So like that, when we replace that, we get this equation is equal to f of x. So taking y, which is on which this whole is operator is to be operated on y, so this equation becomes, so here this equation becomes, okay, replace dn by dx raised to n as capital D raised to n, and here it is capital D raised to n minus 1, capital D raised to n minus 2, y, taking y common, okay, and we get this equation, okay, is equal to f of x. Now we denote this term, that is a0 d raised to n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 plus dash dash plus an into y. Okay, only this can be denoted by f of d. We denote this whole operator. This is one again whole operator. So by f of d. So let f of d is equal to a0 d raised to n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 and so on up to plus an. So let us denote this whole operator by this f of d. So then this equation becomes f of d into y equal to f of x. F of d into y equal to f of x. Okay, so now this is operator d. So this operator d is a differential operator and it satisfies all the rules of a differential calculus. See, differentiation of sum of two functions. Okay, so capital D of u plus v is du plus dv. Next, d raised to m dot d raised to n u is equal to d raised to m plus n u. Means just like applying laws of indices, right? Laws of indices. So d raised to m dot d raised to n u equal to d raised to m plus n u. And similarly, differentiation of a constant into u is same as constant into differentiation of that u. Okay. So similarly, d raised to m of d raised to n u is same as d raised to n of d raised to m into u, where m and n are positive integers. So it satisfies all the basic laws of algebra, right? Next is, here the operator d is not commutative with variables. So for example, d raised to m into u dot d raised to n into v is not equal to d raised to m into v dot d raised to n into u. So commutative means what? Commutative property, already you know, commutative property means ab is equal to ba or a plus b is equal to b plus a. So here d raised to m u into d raised to n v is not equal to d raised to m v into d raised to n u. Okay, so these are the properties of the differential operator. Next, we see some important results, right? So now here we show that a capital F of d, when it is to be operated on e raised to x, it gives e raised to ax into f of a, into e raised to f of a. So these are very, very important results, and these results may ask in the examinations. Okay, in this we see this. Now we prove these results by taking n is equal to 3. So in this equation, okay, in this equation, here this is the equation. Here we take n is equal to 3, and we prove this result. So f of d into e raised to ax, it can be written as, so f of d means already we have taken a0 into, we have taken n is equal to 3, so d3 plus a1 d square plus a2 d plus a3 into e raised to ax. So now this a0 is constant. Next, operate this d cube on e raised to ax. So d cube e raised to ax plus a1 into d square e raised to ax plus a2 into d e raised to ax plus a3 into d e raised to ax. So which is equal to a0. D cube means you have to differentiate e raised to ax 3 times. So you will get a cube e raised to ax plus a1 as it is, then d square of e raised to ax, differentiate e raised to ax 2 times. So you will get a square e raised to ax plus, here it is a2 constant as it is, differentiation of e raised to ax, this is a into e raised to ax plus this a3. So this, where there is no differential operator, so write e raised to ax as it is. So like that we obtain this equation. In all the terms, e raised to ax is common, and we take the e raised to ax common, and we write this one as e raised to ax. And now see here, this equation and this equation are both one and the same, only we have in place of d we have a. This, now see here, in this equation here we have d cube, and after simplifying we get in place of d cube we have a cube. Similarly here a1 correct. Then in place of p square we have a square. Here a2. In place of d we have a3, then e raised to ax. Okay. So here the difference is that it is both one and same, only d is replaced by a. So therefore when this is known as f of d, then this becomes what? F of a. So therefore e raised to ax, and this is nothing but f of a. So this is the proof of the first result. Next, similarly we prove the second one. F of d into e raised to ax into v is equal to e raised to ax into f of d plus a v, where v is any function of x. Now see, f of d into e raised to ax into v is equal to, it can be written as, now already we know f of d is nothing but a0 d cube plus a1 d square plus a2 d plus a3, then write remaining thing as it is, e raised to ax into v. Next again operate this d cube on this one, so a0 d cube of e raised to ax into v plus a1 d square of e raised to ax into v plus a2 d of e raised to ax into v plus a3 e raised to ax into v. Okay. So now first take the first term d cube e raised to ax into v. It is same as now applying the nth Leibniz rule, Leibniz theorem for nth derivatives for product of two functions. So here e raised to ax means a cube into e raised to ax into v plus differentiation of a cube is 3a square into e raised to ax dv plus 3a into e raised to ax into d square v plus e raised to ax d cube v. So after applying Leibniz theorem for nth derivative of product of two functions, so then we get this equation, and again taking e raised to ax common we get this equation. Okay, a cube plus 3a square d plus 3a d square plus d cube into v, or e raised to ax. Now this is the same as d plus a whole cube, because a plus b whole cube is what? A cube plus b cube plus 3ab into a plus b. Okay, so this is nothing but expansion of the term d plus a whole cube. So this is equal to e raised to ax d plus a whole cube into v. Similarly we obtain d square of e raised to ax into v as e raised to ax into d plus a whole square v, and similarly d of e raised to ax into v, it can be this can be obtained as e raised to ax into d plus a into v. Okay, so now substituting all this in this equation, where here, so we found d cube of e raised to ax into v, we found d square of e raised to ax into v, and we found d of e raised to ax into v. Okay, then substituting all this here, and we obtain f of d into e raised to ax v is equal to this equation, or this can be written as e raised to ax. Now again this is similar to again the same, that is this first equation, only the difference is in place of d we have here d plus a. Okay, so therefore this is e raised to ax into f of d plus a into v. So therefore f of d into e raised to ax into v is equal to e raised to ax into f of d plus a into v. Similarly we derive the third result, that is f of d square cos ax is equal to f of minus a square cos ax. Okay, again same. Now write f of d square as a0 d raised to 4 plus a1 d square plus a2. Now here taking n is equal to 2, so then we get this equation, f of d square is equal to a0 d raised to 4 plus a1 d square plus a2. So now f of d square cos ax. So it is equal to f of d square, we know this is f of d square into cos ax. Again operate each differential operator on cos ax. So which gives a naught d raised to 4 of cos ax plus a1 d square of cos ax plus a2 cos ax. So on differentiating here, d raised to 4 means we have to differentiate this 4 times, d square means we have to differentiate this 2 times, then here there is no differential operator, write as it is. So after obtaining, we get this as a naught into minus a square whole square plus a1 into minus a square plus a2 into bracket cos ax. Now see again, this is similar to this operator. Now see, in place of d we have a, that is sorry, minus a. In place of d we have minus a, and all others quantities are same. So a naught is a naught. In place of d we have minus a, so that it becomes minus a raised to 4. Then a1, but in place of d we have minus a square. So we here in place of d square we have minus a square, in place of d raised to 4 we have minus a square raised to square, and a2, then again same. So therefore this is nothing but f of minus a square cos ax. So therefore f of d square cos ax is equal to f of minus a square into cos ax. Similarly, we prove f of d square into sin ax is equal to f of minus a square into sin ax. Okay, so with this important results, I conclude this class and I'll continue in the next class. Okay, thank you.